All right, so earlier in this chapter, we started talking about dimensions and units, and we gave very simple examples of, what types of dimensions do different physical quantities have, and how do we convert from one set of units to another. And I kind of made this comment that if that's all you think about dimensions and units, you're missing out on an incredibly powerful way that just thinking about the dimensions of physical quantities gives us to help understand the world around us, right? So even if all you know are things like physical quantities have dimensions attached to them, you can immediately use that knowledge to start deducing relationships between how different things in the world work. So for instance, you can say, suppose I take a softball and I throw it, and then I throw it with twice as much force. You can use dimensions to immediately figure out, even not knowing, what some of the underlying physical laws are. Do you expect the ball to travel twice as far, 4 times as far, half as far? You can start working these things out, Or similarly, you can start figuring out, maybe you have a pendulum, a mass hanging like this, and it's swinging back and forth. And you can ask, what determines how long it takes for a pendulum to swing back and forth? And implicitly, why were pendulum clocks used so much for so many years, right? So I want to start talking about, how you get to that stage. How do you go from thinking about dimensions to using dimensions to deduce, shortcuts to physical laws underlying the world around us? Okay. So let's start out with the basics of dimensional analysis. So 1.4.1, basics of dimensional analysis. Okay, and the basic idea here is that physical quantities, again, have dimensions associated with them, and there's kind of an arithmetic to how dimensions and how units work, right? And so, one thing is, suppose you have some random equation, x is equal to some other things, y plus z. If these are physical quantities, all of the dimensions of all of these things have to agree with each other. So you immediately know things like the dimensions of the quantity x, remember we're using these brackets to mean the dimensions of the thing inside, has to be the same as the dimensions of the quantity y, and it also has to be the dimensions of the thing of quantity z, right? And that's because, you can multiply objects together that have different dimensions to get a new quantity that has kind of combined dimensions in the same way that we said, so multiplication. Remember we said, or we'll introduce it soon enough in this course, that a force is like a mass times an acceleration. And that means the units of force are given by the units of mass times the units of acceleration. And we said the dimensions of mass was the script m, the dimensions of an acceleration was like a distance divided by a time squared. Okay, so you can multiply things like this, but you can't add things that have different dimensions associated with them together and get a physically meaningful quantity. For example, if I say I have 1 meter plus 1 kilogram, this just doesn't make sense. This is like some undefined load of nonsense. And so the fact that dimensions have this kind of arithmetic associated with them lets you do a bunch of neat tricks just thinking about dimensions. One of the simplest things that you can do with this dimensional trick is just to kind of check your work as you go along. If you have some expression, you've written down an answer, and you look and you see that you're summing together or you're subtracting quantities that have different physical dimensions, you must have made a mistake at some point along the way, right? It can also help you remember, what different, things that appear in some of your equations actually mean. So for example, so this is like dimensional analysis to help remember formulas, help remember stuff. For example, Newton's law of gravitation tells us that the force exerted by 2 objects on each other due to gravity is given by the following expression. There's some constant g, Newton's universal gravitational constant, multiplied by the mass of object 1, multiplied by the mass of object 2, divided by the distance between those 2 objects. So, if this was the sun and the earth, mass 1 would be the mass of the earth, mass 2 would be the mass of the sun, and r would be the distance from the sun to the earth at that particular moment in time, right? And suppose you don't really remember, well, what does this g even mean? What are the units associated with it? What's going on? You can use simple dimensional analysis to answer that question for yourself, right? Because dimensional analysis tells us that the dimensions of each side of this expression have to agree with each other in order for the whole thing to make sense, right? So the dimensions of force have to be equal to the dimensions of whatever this combined thing is, g, m1, m2 over r squared, right? And we know what the dimensions of most of these things are. So the dimensions of force, well, we just talked about that up above. That's going to be a mass times an acceleration. So that's a mass times a length divided by a time squared. So let me just write that as t to the minus 2. And what are the dimensions of this whole thing? Well, this is going to be equal to the dimensions of g multiplied by the dimensions of m1, m2 divided by r squared, right? So that's dimensions of g multiplied by, I guess I have 2 powers of mass, so that's mass times mass, divided by 2 powers of length. This r squared has units of inverse length. So I could write that again as L to the minus 2, okay? And then remember, I can kind of treat dimensions in an algebraic way, so then I can solve for dimensions of g. And what I get is the dimensions of g. So I'm going to bring 2 powers of mass to this side, I'm going to bring 2 positive powers of L to the other side, and I'm going to end up with mass to the minus 1. The time thing stays the same, so that's going to be time to the minus 2 times L to the 3. So this was kind of a trivial and perhaps not particularly enlightening example of just how you do these kind of arithmetic of dimensions and how you can think about the various subquantities that appear in some of your expressions, just with the constraint that the dimensions of different quantities in an equation all have to agree with each other, right? So this version of dimensional analysis probably still feels kind of a bit dry, right? A bit like a bookkeeping technique, just to make sure we haven't accidentally written down an equation incorrectly, so on and so forth. As promised, though, this is really a gateway to physically understanding lots of things in the world around us. And it's especially powerful when you start combining dimensional analysis together with some of the sort of estimation techniques that we talked about in the previous sections. So that's going to be this video, but in the next set of video recordings, I'm going to walk through 2 case studies. First, we'll talk about how just from a photograph of one of the first atomic explosions in history, you can infer how powerful nuclear weapons are without knowing anything, basically, about, nuclear engineering, atomic energy, anything, just by looking at a picture and applying dimensional analysis. And then I'll take a more prosaic example after that, kind of a less violent example, more in the everyday world. I'm sure you've looked at you've looked out the side of a car window when it's been raining, and you've noticed little raindrops forming tracks diagonally across the window. And you can use these dimensional analysis techniques to ask yourself questions like, just by looking at the direction that a droplet is going, can you figure out how fast your car has to be going? So we'll see those 2 examples of the power of dimensional analysis in the next set of videos.